Hey guys, and welcome back for another lesson on functions. Today we're looking at graphed curves of functions to see how a function like this can be turned into a function like that. My name is Ms. Danielson, and let's get started. You should already be familiar with these types of transformations. Translation, which is simply shifting that congruent shape to the left, to the right, up or down. Reflection in a line. Generally, we'll be looking at the x and y axis as our mirror lines now. Rotation and enlargement. However, for transforming functions, we're not going to look at rotation or enlargement. We'll only look at translation and reflection both horizontally and vertically. We're also going to look at a different type of transformation called a stretch. And again, this could be a vertical stretch or a horizontal stretch. Let's start right in with an example. Now, usually they won't actually tell you what the function is. They'll just give you a graph of its curve and tell you that the y coordinates on all of the points on this curve are equal to the output of the function. For the sake of our understanding here, I'm going to tell you that this curve is our basic positive parabola. So my function f is simply x squared. Now we're going to sketch a graph of y equals f of x plus 2. So to do this, let's have a look at our basic table of values for y equals f of x. When x is -3, f of x would be -3 squared, which is 9. When x is -2, f of x would be -2 squared, which is 4, and so on. So I filled in this table of values for you so that we could then see what y equals f of x plus 2 would look like. If the second row here is f of x plus 2 must simply be 2 higher than that. So when x is equal to -3, f of x is equal to 9, so f of x plus 2 must be 11. And I do the same thing for each of my coordinates. Now, if y is equal to f of x plus 2, that means that all of my y coordinates are now 2 higher than they were previously. Seeing this on the graph, you should notice that each of the coordinates have been shifted upwards 2 units. What this tells us is when we see a vertical change in our graph, that's because somehow the y coordinates have been affected. However, when we're translating functions, you'll notice this when we've got some kind of change outside the brackets. I've added 2 to the function, not inside the brackets, not to the input, but outside the brackets, so it's affected my output. So we've just learned our first type of transformation. If we've got y equal to some function, and then we add or subtract something after that, outside the brackets, that's going to translate our function vertically, so up or down, the same number of units as we are adding on outside the brackets. If a is positive, this is going to be an upwards translation. If a were negative, this would be a downwards translation. Let's see another example. Now, as you can see from this graph, the curve is not the same as the previous one. F of x could be any type of curve. And again, for the sake of our understanding, I'm going to tell you that this is our basic cubic curve, where f of x is simply x cubed. So if y is equal to f of x, and we want to sketch y is equal to f of x plus 2, this time we're adding 2 inside the bracket. I bet you could probably guess at how this is going to look, but let's be careful with this. Let's have a look at our table of values again. So for values of x between -3 and +3, f of x are those values cubed. So -3 cubed, -2 cubed, -1 cubed, 0 cubed, 1 cubed, 2 cubed, 3 cubed. However, if I wanted to work out what f of x plus 2 would be, simply think that this was f of -3. When x is equal to -3, x plus 2 would be -1. So we're working out f of -1, f of 0, f of 1, and so on. Now this may seem like more work, but notice that we've actually already done this up above, just in a different place. So y equals f of x plus 2 would simply be the same y output values as we had from above. However, they go along with a different input value. When x was -3, f of x plus 2 meant f of -1, which I'd already worked out over here. I've got the same output values, the same y coordinates. However, they are grouped with different x coordinates. Notice the pattern here. I'm working out f of negative 3 plus 2, but the output is the same of f of negative 1. F of negative 2 plus 2 is the same as f of 0. So this is going to shift my graph, but which way? Was that what you had expected? All of my coordinate points have been shifted 2 units to the left. That's 2 units in the negative direction. Well, I'm sure most of you were expecting it to shift 2 units to the positive side, to the right. So this is an important lesson to jot down. When our graphs are affected horizontally, that's when we have changed the x coordinates, or we've made some kind of a change to the expression inside the bracket, our graph will be affected horizontally. But watch out, because that means it's changing our x coordinate. And you might remember it this way, your x never does what you expect. That might be why you broke up. So a general rule we could write down is that when we work out what y equals f of x plus some number inside the brackets, it will be a horizontal translation by negative b units, or a translation by the vector negative b over 0. If b is a positive value, the translation will go to the left, the negative direction. Whereas if b is a negative value, then the translation will be to the right, the positive direction. We've still got several other types of transformations to discover. So let's see another example. As you can see, I've given you another cubic curve here, which I'm calling function f. And usually you won't be told what function f is. But again, for the sake of our understanding, I'll tell you that f of x is x cubed plus 2x squared minus 2x. Now I want to sketch the graph of negative f of x. Notice that my negative sign is outside the brackets. That means it's going to affect my graph vertically. Let's have a look at a couple of the points. Since I know that negative 1.7, 4.3 is on the curve of f of x, I know that f of negative 1.7, so that's when x is equal to negative 1.7, the output is 4.3. For the transformed version of that graph, for negative f of x, I should then know that if f of negative 1.7 is 4.3, negative of f of negative 1.7 should be negative 4.3. So that gives me a point on this transformed curve. I know that negative 1.7, negative 4.3 will be a point on my transformed curve y equals negative f of x. So I've put that point down here. Similarly, if I know that the point 0, 0 is on the point here, I know that when x is equal to 0, and I put that into function f, the output is 0. So if I'm going to work out negative f of x, if I put 0 into the function negative f of x, my output should be negative 0, which doesn't really exist, so it's going to be 0 as well. That means that 0, 0 will also be a point on my transformed graph y equals negative f of x. So I'll put that point here. Next, if I know that the point 0.4, comma negative 0.4 is on my graph y equals f of x, that's over here, then I know that when I put 0.4 into my function f, my output is negative 0.4. So similarly, if I put 0.4 into my function negative f of x, I should get positive 0.4 as my output. I simply changed the signs on both sides of that equation. So that means the point 0.4, 0.4 will be on my graph of y equals negative f of x. That's this point here. You should be getting the idea of where these points are ending up. This first point up here at negative 1.7, 4.3 ended up down here at negative 1.7, negative 4.3. This point here, which was on the x-axis at 0, 0, stays on the x-axis at 0, 0. And this point here, which was at 0.4, negative 0.4, is now on the other side of that x-axis at positive 0.4, positive 0.4. Let's see what that curve is starting to look like. Is that what you would have expected? I hope so. Noticing that that negative sign was outside the bracket, it has affected my graph in a vertical way, and it simply changed my y coordinates from positive to negative or from negative to positive. And of course, my point 0, 0, that was neither positive nor negative, stayed on the x-axis. So we can say that a transformation involving putting a negative sign outside the bracket in front of the function will simply reflect that curve in the x-axis. Next up, we've got another cubic curve, but it's a different one. And again, we're not usually told what the function is. However, we should be told some of the important key points. Here I'm telling you what the maximum point is. I'm telling you what the y-intercept is. I'm telling you what the minimum point is. And here are a couple of other points just to give you an idea of the shape of the curve. So once again, if I want to transform this curve into the curve y equals f of negative x, note that this negative is inside the brackets this time. So we should know that this is going to affect my graph horizontally. I'll bet you could probably already guess at how this is going to look, but let's go through a couple of points just to be sure. Since we know that negative 1.73 is on the curve y equals f of x, that's here, we know that f of negative 1.7 is equal to 3. When my input is negative 1.7, my output is 3. Logically, that means that f of negative x will be equal to 3 when x is simply positive 1.7. So if I put positive 1.7 in here, I'll have f of negative of my 1.7. This tells me that when the x value is positive 1.7, the y value will be 3. So 1.7, 3 will be a point on my graph y equals f of negative x. So I'll put that point over here. Now you already see this point plotted here, but remember that I plotted this point now by using this coordinate point and transforming it over to here. Let's try another point. If x is equal to negative 1, y is equal to 5. That's this point up here. That's a point on my y equals f of x curve. So if I know that when I put negative 1 into function f, I get an output of 5, I should be able to reason that f of negative x would be equal to 5 when I put 1 into that transformed function. So f of negative of this 1 would give me that same output value, that same 5. That tells me that 1, 5 will also be a point on my graph y equals f of negative x. So when I'm looking at this point here on my original graph y equals f of x, it transforms to this point over here on my graph of y equals f of negative x. One more point, if x is equal to 0, y is equal to 3. That is when I put 0 into my function f of x, I get an output value of 3. And that shows me this point here, the point 0, 3 on my red curve. What that tells me is f of negative x is equal to 3 when I put 0 into my function f of negative x equals 3. So that's the point 0, 3. Again, that's a point that was already on my graph. It's that point right there. So when I put 0, 3 through this transformation, it did not move. However, this point here was moved over to here, and this point here was moved over to here. Can you see what's been happening? Point 1, 1 would have been moved over to here, and point 1.7, 3 would be transformed over to here. Can you now see what's happening? Let's see that curve. That curve is simply a reflection in my y-axis. Y equals f of negative x. Inside the bracket, we've changed that value to negative. Will be a horizontal reflection in the y-axis. Two more examples now just to show our new type of transformation, the stretch. Here again, I've got a positive cubic curve, and I'm telling you, just for the sake of this example, that f of x is equal to x cubed plus 1. So if I want to sketch y equals 2f of x, notice that that 2 is outside the bracket, so it should affect my graph vertically. Let's see a couple of those points. If x is equal to negative 3, negative 3 cubed is negative 27, plus 1 gives me negative 26. So I've completed my table of values, simply cubing the input value, cubing the x value, and adding 1 to it. Now, if I want to graph y equals 2f of x, I'd simply be graphing the y coordinates, which are 2 times the previous y coordinates. I'm sure you can imagine what that's going to look like, but let me just show you. What you should have noticed is that my curve seems to be stretched upwards, but it's also stretched downwards. Note the negative 26 has become negative 52. What's happened here is all of the coordinate points have been stretched vertically away from the x-axis by a scale factor of 2. That is, we have doubled the distance of each of these coordinates from the x-axis. A nice easy way to write that is simply y equals some value multiplied by f of x, since that value is outside the brackets, vertically stretches the graph by a factor of c away from the x-axis. And I'll bet you can guess at what our last example is going to demonstrate. Again, we are going to stretch this function, but horizontally. Sketch the graph y equals f of 2x, but now the 2 is inside the brackets. That affects my graph horizontally. Let me show you a table of values for the graph y equals f of x. Again, I've just cubed the x value and added 1 to it. So for example, 1 cubed is 1, plus 1 makes 2. 2 cubed is 8, plus 1 makes 9. Now I want to show you what y equals f of 2x will look like. First of all, f of 2x would be f of the x value multiplied by 2. So this would be f of negative 6, f of negative 4, f of negative 2, and so on. I've simply doubled the input value. I've doubled the x value. Now to work out what f of 2x would be like, I'm going to need to do f of negative 6. So negative 6 cubed plus 1. Negative 4 cubed plus 1, negative 2 cubed plus 1, and so on. Now, while most of these values are new, and some of them are quite a bit bigger than ones we previously, while some of them are quite a bit smaller, that is more negative than we've previously seen, we have seen some of these y coordinates before. In fact, if you look at where we're seeing them from, you'll see they've sort of squashed in towards the middle here. Let's have a look at how that looks on our graph. Notice that my blue curve has similar y coordinates to my red curve. However, they occur at points closer to the y-axis. My curve has been squashed in. All of the x coordinates are half the size as they were on the red curve. An easier way to explain this or write this is to say that y equals f of some number times x is a horizontal stretch, and I'm putting this in quotations here because some of you might say this hasn't been stretched, it's been squashed. Still, just like enlargements, whether they're getting bigger or smaller, we still call this a stretch even though the factor might be a fraction. Remember that thing about your x? Never does what you expect. When we multiply by the x inside the brackets, our graph actually looks like our x coordinates have been divided by that factor. Now, I hope you've taken the time to make a note of all the different types of transformations we've discussed today. If not, you might want to skip back now and do that before we get into the practice part of this lesson. Here I've got a positive parabola for you, and I've labeled the key points, the roots, the minimum point or turning point, and the y-intercept. Now, those coordinates are really important because I want you to tell me where those points will end up once I've transformed this function in various different ways. Even though I'm not telling you what the function was, you should be able to tell me how these points get transformed through the transformations of subtracting some value outside the bracket, adding some value inside the bracket, dividing the input value by 2, making the input value negative, or making the whole function negative. Go ahead and hit pause now and give that a go, and hit play when you're ready to move on to the next question. Here we've got another curve, a positive cubic, which I'm going to transform in 5 different ways. Once again, I've given you some critical points. I've given you the roots, I've given you the maximum point, the minimum point, and the y-intercept. And you're going to need to tell me where these coordinates end up after these transformations. I might add something outside the brackets or subtract something inside the bracket, multiply by something inside the bracket, make the value inside the bracket negative, or here's a challenging one. See if you can give it a go. 1 minus that function. That's 2 separate transformations in one go. Go ahead and hit pause now and give it a try, and hit play when you're ready to take up the answers with me. For this first graph, my positive parabola, a transformation by subtracting 2 outside the brackets will be a vertical translation down 2 units. Now I'm only asked to work out my new y-intercept and my new minimum point because they are simply going to shift down 2. However, by shifting the whole curve down 2, it'll be very difficult for me to work out my new roots. By adding 2 inside the brackets, that's going to affect my x-coordinates. But remember, my x never does what I expect it to. It's affecting it in the opposite way that I would expect. Rather than my x-coordinates getting 2 higher, they'll go 2 lower. That's a horizontal translation, 2 units to the left. Next, when I divided x by 2 inside the brackets, that's obviously going to affect my x-coordinates, but in the opposite way that I expected. So rather than having half their value, they're actually going to have double their value. This is going to be a horizontal stretch by a factor of 2. So the distance from the x-axis is now getting twice as big. My new y-intercept, which was previously on the y-axis, so its distance of 0 from the y-axis, remains on the y-axis, still a distance of 0, or 2 times 0 from the y-axis. Next, if I were to sketch y equals f of negative x, that negative is inside the brackets, so it's affecting my x-coordinates. That's going to be a horizontal reflection in the y-axis. So my previous root, negative 6.50, will move across to the same distance on the other side of the y-axis to positive 6.50. My other root, negative 0.50, moves across the y-axis to its new position at positive 0.50. My minimum point also reflects across the y-axis. Its previous distance from the y-axis was negative 3.5, so its new position is positive 3.5, negative 9.3. And my y-intercept, which was on the y-axis, remains on the y-axis. So my new y-intercept is still the point 0, 3. Next, if I were to graph y equals negative f of x, that negative is outside the brackets, so this is affecting my y-coordinates. Each of these points will reflect across the x-axis. My 2 roots will not change because they were on the x-axis. My minimum point, however, will become a maximum point, and my y-intercept reflects into the x-axis down to the point 0, negative 3. Onto our second curve now. If I were to add 4 outside the brackets, I know that's going to affect my graph vertically. It's going to affect the y-coordinates. And that's going to be a translation of 4 units up. So my previous maximum point will move up 4 units to the point negative 2, 8. My previous minimum point will move up 4 units to the point 0.8, negative 4.2. And my previous y-intercept will move up 4 units to the point 0, negative 2. If I subtract 5 inside the brackets, I know that's going to affect my x-coordinates. So that's going to affect my graph horizontally. However, it will affect my graph in the opposite way to what I might expect. My x never does what I expect. It's going to translate my graph 5 units to the right. That's 5 units in the positive direction. My previous root, negative 3, 0, will move 5 units to the right to the new point, 2, 0. My previous route, -1, 0, will go 5 units to the right to the point 4, 0. And my previous route, 2, 0, will move 5 to the right to the new point. Oopsie! There's a mistake here. Can you spot it? Next, my maximum point will shift 5 units to the right to the new point 2.9, 4. And my new minimum point will shift 5 units to the right to 5.8, -8.2. For part C, if I multiply by 2 inside the brackets, my graph will be horizontally stretched by a factor of 0.5, or a half. The distances from the y-axis will be halved. So my new curve will look like this. As you can see, my routes have gotten closer to the y-axis. My first route is now at the point -1.50. My next route is now at the point -0.50. And my third route is now at the point 1, 0. My previous maximum point has moved closer to the y-axis as well. This is now the point -1.054. And my previous minimum has also moved towards the y-axis, is now at 0.4, -8.2. My y-intercept, however, was on the y-axis and it hasn't moved. It's still at 0, -6. Question D, we should be familiar with this one now. If I make the x inside the bracket negative, that's going to affect my graph horizontally. It's going to reflect in the y-axis. So all of my x coordinates will go from negative to positive or positive to negative. My y-intercept stays on the y-axis at 0, -6. Finally, our super challenging one. This is 2 different transformations in one. I hope you gave it a go on your own first. I'm going to show this to you in 2 separate steps. So if y equals 1 minus f of x, my f of x function is now negative. That's a negative sign outside the bracket. That's affecting my y coordinates. That's going to reflect my graph vertically in the x-axis. So let me start by doing that. So that's moved all of my y coordinates from the negatives up to the positives and from the positives down to the negatives. My roots stayed in the same place because they were on the x-axis and a reflection in the x-axis didn't move them at all. Next, I need to add 1 to this function because this is 1 minus f of x, not just minus f of x. So I'm going to shift that graph vertically upwards 1 unit, as you see here in black. So my new minimum point, which was previously at -2.1, -4, is now 1 up from that, so it's -2.1, -3. My previous maximum point, which was at 0.8, 8.2, has moved up 1 unit to 0.8, 9.2. And my previous y-intercept, which was at 0.6, has moved up 1 unit to 0.7. Now, how did you do with that? I'll bet that last question was a bit of a challenge for you, but it's always good to test yourself to the highest level. So please let me know down in the comment section what level you think you're at. And till next time, just keep practicing and I'll see you soon. Bye.